tonight. So it is a real pleasure to have my former advisor, the one and only Umesh Vazirani, should need no introduction, to tell us about quantum Hamiltonian complexity.
Thanks, thanks, Scott. From the one and only Scott. That's so. You know, I have been on the the way I think about it. The Hebrew University has had us. I think of it as a quantum computing center since at least the late 90s, with this wonderful work by Mickey and Dorit. So it's a great thing that you formalized it 15 or 20 years later, and nice to know. So let me say what here's sort of the maybe the main picture of what I'll talk about. So I'm sure you all know that quantum computing teaches us that quantum systems are exponentially complex. Thanks. So here's what that means. So what it means is if you have a system of n particles classically, you can describe them using order n parameters, like the position and momentum of each. But if you have a quantum system of n particles, you need exponential in n parameters. Now, let me clarify what I mean here. So, of course, if you have a classical system, you might choose a more complicated representation of it. For example, you might not know what the positions and momenta are, or it may be that your state of knowledge is not so certain, and so you have to describe the system by a probability distribution. That's your limitation if you don't know it, right? In the case of a quantum system, as far as we know, there's no alternative but to describe it using exponential amount of information. Okay? So how do we know that? Well, the answer is we don't, for sure. But the best evidence we have that it takes exponentially many parameters is a computational evidence. It's because a quantum system has exponential power computationally on certain problems that we know that if you were able to describe a quantum system using polynomially many parameters, then you would automatically speed up the computation. So this is our best evidence that this exponential here is necessary. And obviously it has this wonderful implications for computation. But then you could sort of ask, given that the computational power already reveals to us something very interesting about the nature of a quantum system, namely the necessity of this exponential description, you could ask, well, what else can we learn about it? And in fact, the other side of this coin about the exponential power is also the fact that this exponential description provides an exponential obstacle to analyzing and understanding quantum systems. Okay, and so this is the piece that I want to focus on today. Okay, so now you could still say, well, maybe not all quantum systems are implicated in this way. Maybe there are some simple quantum systems. In fact, we believe that classical systems are also born of a quantum in a quantum universe. So what we'd like to do is try to understand a corner of Hilbert space, right? So this exponential dimensional space where the state of an n particle system lives. We want to understand whether there's a corner of it which is actually simple. And if you want to be extremely ambitious, you might even say, well, maybe natural systems, systems that occur in nature, happen to live in this corner. Okay, so that would be an extremely ambitious thing to try to hope for. And of course, then there are complexity theorists who really don't like the idea of quantum computation and believe that, in fact, this whole exponential Hilbert space is just, it's just the physicists sort of getting too carried away. So this would also be a good thing for those people to think about, because this could be for them a way of showing that, in fact, not only naturally occurring states, but also any states we could hope to create lie in some corner of Hilbert space. And so, maybe quantum mechanics itself is this small. It needs to be revised to be this small. Okay, so, yeah.
When you say small, you mean classically simulated?
Yeah, I mean that instead of needing exponential amount of information to describe them, you can describe them in polynomials, using polynomial amount of space, and then you should be able to simulate and so on. You could sort of pile on the requirements, but I'll keep the requirements vague and just say, well, do we have polynomial exponential complexity? Okay, so yes.
This will be probably also a result of the dimensionality, because for small dimensions we know it's not true.
Small dimensions meaning?
Like small Hilbert space.
Well,
small dimensional Hilbert space.
Well,
when n is small, we know that it's not true. Nature occupies all of it.
Well, when n is small, we have trouble distinguishing between polynomial and exponential. It's an asymptotic notion. So yeah, you're right that you have to make this distinction somewhere. But what I'm sort of assuming here is exponential grow. The exponential functions grow so quickly that already at a few hundred, n of a few hundred, it's a ridiculously large number. So instead of thinking of it as a quantitative difference, I want to think of it as a qualitative difference. Okay, so in particular, one way to start investigating this question is to start to think about, well, what about ground states of local Hamiltonians, or ground or low energy states of local Hamiltonians in general? So one thing we could ask is, if you have a particle, if you have a lattice of n particles with nearest neighbor interactions described by a local Hamiltonian, is it necessarily the case that the ground state has a polynomial description? Or if not, can we make a meaningful question out of it by restricting in some way? Okay, and so unfortunately, there's a trivial answer. The trivial answer is, of course, there's a polynomial description, because all you have to do is to say, describe the local Hamiltonian, because each term is a local interaction. You can describe it using a constant amount of information. And then the number of terms is clearly bounded by a polynomial. So you could describe the polynomial and then say, I am interested in the unique ground state of this Hamiltonian. So that's a perfectly good description, right? It's it's like this joke about mathematics, that it gives you results which are precise, completely proven, and sometimes they are totally useless. So here you have a result which is totally useless. So we could step back again and see, what is it that we want from this polynomial description? So what we really want is a polynomial description that allows us to compute interesting quantities about the state. And so the quantities we want are things like 2-point correlations, or the ground energy, or the result of some local observable on this state. So now this is exactly this field of quantum Hamiltonian complexity. It's sort of the place where condensed matter physics meets quantum complexity theory, and it's a beautiful area. So what makes it beautiful is that at this intersection sits the two basic questions, one from this side and one from this side, and moreover they turn out to be essentially the same question. So this is what really makes this area so interesting. So the two questions are these. So on this side of condensed matter physics, it's local Hamiltonians, and on the side of complexity theory, there's this very fundamental question called constraint satisfaction problems, or satisfiability, where you have n Boolean variables and a number of constraints on them which are local. They each involves, say, 3 variables or 4 variables, and you want to know whether you can satisfy all of these, or what's the maximum number you can satisfy. And it turns out that there's a complete dictionary between these two sides. So what does the dictionary look like? Here you're interested in the number of unsatisfied clauses. There it's the energy. Solution corresponds to ground state. And on the classical side, you're interested in these questions because this is the class of combinatorial optimization problems. It's a very rich and beautiful class of combinatorial optimization problems. And out here, ground and low energy states, that they determine properties of materials. Okay, so So now this dictionary, of course, keeps going on. It's been known since what is it, the 70s, that these problems here, like satisfiability, are NP complete. And Kitaev showed in, I guess probably about 15 years ago, that the problem of estimating the energy of such a local Hamiltonian is QMA complete. So the class QMA corresponds to the class NP. So in the class NP, what we say is that, even though the solution is hard to find, if somebody were to give you the solution, you can easily check. So here also, the solution is hard to find, but if somebody were to give you the solution, it's easy to check for a quantum computer. So, and the solution itself is a quantum state. Okay, but the thing about complexity theorists, if you don't know already, is that we have opinions about everything and knowledge about almost nothing, and so there are many conjectures in complexity theory which the world is all mapped out and it all makes sense. So here the conjecture is that QMA is not equal to NP, and that in fact for a QMA complete problem there should be no sub-exponential size classical witness. Right? So here you have a polynomial size classical witness that you can check easily. Here you have a polynomial size quantum witness, but the conjecture is that there's no classical witness that's less than exponential size. Okay, so what that says is that we had better restrict this class further. Ground states of local Hamiltonians still require this exponential description. So to get away from this curse of exponentiality, we'll have to restrict the problem further.
So just to understand the conjecture better, under no representation, there's no way to compactify it in any way. That's the conjecture.
That's the conjecture. Right. Again, it's computational. It says, you cannot get such a witness. This is a witness, and you cannot
change basis.
In such a way that you could compute the energy efficiently.
And we should say, and you're even allowed a quantum computer to verify the classical.
For example.
I have a question. So these two classes are really beyond NP complete, right? So NP complete and QMA is even more complicated. So how can it be relevant to condensed matter physics when you're talking about such high-level computational classes?
Physicists are just more, they're more ambitious than us.
No, but this is something that even a quantum computer cannot.
The reality is rich.
There's amazing results saying, a real problem is hard unless QMA equals NP.
It's equivalent, So Gil, I think I understand what you're saying. So NP completeness shows up in many places in classical physics, but these are problems that you want to solve, and you end up saying, well, actually you have a heuristic, you can find so it's a way to guide your search, and QMA completeness is a similar way to guide one's search. So it's of course it's a first step, and then you want to simplify and you want to say, of course we are not going to go there. Let's try to find a path that gets us to somewhere. Right? Does that help? Yeah. Okay. So okay. So while I'm here, let me touch upon one vignette quickly, which is one of the greatest results of complexity theory is the PCP theorem, which says that in fact it's even NP hard to approximate a solution to such a constraint satisfaction problem. Meaning, if you're given a Boolean formula, it's even hard to tell whether it's completely satisfiable, all the clauses are satisfiable, or whether there's no way to satisfy more than 90% of them. And so you could ask, is the same thing true on this side? Namely, is it possible to tell whether, given the Hamiltonian, whether the lowest energy state has energy 0 or some fraction of m, 0.1 m or something? So that would be the natural analog of the PCP theorem, and we do not know whether this is true or false. Okay, and so unlike most things in complexity theory where we have a very strong opinion one way or the other, here there isn't a strong opinion. It's So it could go either way, and we don't really know. There are a lot of partial results about this, but I'll sort of skip those for because I want to get to other stuff. One way you can interpret this question is you can sort of say, is it possible that quantum systems exhibit exponential complexity even at high temperature? Okay, so okay, that's as much as I want to say about that. And now I want to get back to this question about how do you actually come up with a simplification of this question that takes you away from exponential complexity. And so after Kitaev's result, there were a number of simplifications of this result, which eventually led to this beautiful result by Aharonov, Gottesman, etc., which sort of said it's even QMA complete for 1D Hamiltonians, which means you have particles interacting with each other on a line, nearest neighbor interactions on a line, and even there it's QMA complete. And so, that it's not clear how much easier it can get than this. And then, just to add insult to injury, there was this final piece which said it's in fact even hard, not QMA hard, but hard in some sense, even for translation invariant 1D Hamiltonians, which means that all your local terms are the same. Okay, so at this point you might, we can step back and see what are the lessons from complexity theory. It tells us that finding these low energy ground states is QMA hard for very simple systems. But then on the other hand, you could sort of ask, well, how do condensed matter physicists ever deal with quantum systems if even the simplest ones are easy? And so, well, of course there are various approximations which may be questionable, but then there's this one heuristic by Steve White, DMRG, which has been applied very, very successfully to 1D systems in practice, and over the last 2 decades. And so you could ask, is there sort of, can we explain the success of DMRG by showing that, in fact, 1D systems in some natural restriction are actually easy? So the hint about what the crucial parameter is came in this work, where the crucial parameter is a spectral gap. So it's the gap between the ground energy and the first excited energy. So if you look at the constructions of these QMA complete Hamiltonians, the gap scales as 1 over polynomial in n. Whereas there's this natural subclass, which is the gap local Hamiltonians, where the spectral gap is a constant. So let me sort of explain the normalization here. So I'm assuming that the norm of each local term of the Hamiltonian is 1. So when we say that the gap is a constant, what that means is, so if the ground energy is 0, then the first, E1 might be 1 over 10, which means on average 1/10 of a term of the Hamiltonian must be violated by any state. Okay, so or if you want to think about the classical intuition, then for classical satisfiability, if the formula is not satisfiable, then the least that must happen is that there's one clause that's unsatisfied. So the gap would be 1 there. Right? Yes?
Can you explain the second point, that QMA complete Hamiltonians?
Well, if you look at those constructions, then the gap happens to be 1 over poly n.
These are two different. This is the promise gap. It's not the spectral gap.
Yeah, but if you look at I think if you look at the actual spectral gap,
There are 2 solutions, for example, and 2 states have 0 in it.
well, then the gap is 0, right?
So if you have something that's accepted with probability 99%, I don't know. I don't see why
This 1 over poly is less or equal or greater to 1 over poly?
It's less than or equal to.
Less than.
It's equal. Yeah.
Less than or equal.
Yeah.
Okay.
Yeah. Okay. So this subclass is one where the gap is large, right? It's actually a constant as opposed to that small. Sorry. Okay, so in 2007, Matt Hastings showed this, he showed that ground states of 1D Hamiltonians, ground states of gapped 1D Hamiltonians have polynomial representation as a matrix product state. And therefore, if you look at gapped 1D Hamiltonians, finding this ground state or approximation to it is an NP, because you can guess it, and you can guess this matrix product state. Okay, but then the folklore about this was that it's actually hard to find such a representation. And in fact, there was a paper by which showed that a closely related problem is NP hard. Okay, so on the other hand, what happened recently is last year, in trying to strengthen Hastings' result, we showed that in fact there's a sub-exponential time algorithm for this, for finding these ground states, for finding this representation, and
Of what complexity?
it was 2 to the. It was exponential in. Sorry, it was 2 to the 2 to the square root. No, log to the 2/3. Log to the 2/3. Okay. 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 And then earlier this year with Zeph and Thomas, we showed that in fact there's a polynomial time algorithm. So this was really a bit of a, so once you have a sub-exponential algorithm, you don't expect the problem to be NP complete, and so it was a reason to think one should.
But that's only to get a 1 over Pauli. Oh, is that, sorry, is that a 1 minus 1 over Pauli approximation?
Yeah.
All right, so it's a good approximation.
Yeah. Okay, so so now let me just very quickly sort of explain some of the some of the thinking behind these results. So, of course, the main obstacle to describing quantum states succinctly is entanglement. So, for example, if you have a bipartite state, if you divide your state into 2 parts, then you can always write the state using a singular value decomposition or Schmidt decomposition as a superposition over product states in some orthonormal basis, right? So basis AI for the A space and BI for the B space, and then the Schmidt rank, which is a very crude measure of entanglement, just says how many such terms do you need in this decomposition, and that's a measure of your entanglement. And then there's of course a more subtle measure of entanglement, which is the von Neumann entropy, which is just the classical entropy of these CI squareds. So if some of the CIs are very small, they'll still contribute to the Schmidt rank, but they'll contribute very little to the von Neumann entropy. And so what makes all of these results work is this beautiful conjecture from condensed matter physics called the area law. So what this says is that if you have a gapped local Hamiltonian and you look at the ground state of this local Hamiltonian and you partition the particles into 2 subsets, so say this one and the outside, then what it says is that the entanglement entropy of the ground state scales not like the volume of this region, which is the number of particles in here. That's the trivial bound. But instead, it scales like the surface area of the cut. Okay, morally, what it says is that the entanglement, most of the entanglement sits near the boundary of the region. And so if this were true, then you could imagine that to describe the ground state, all you have to do is describe the entanglement near the boundary, which you could do succinctly, and then you describe the state inside and outside separately. And so this is exactly what a tensor network does nicely. It helps you get such a description nicely. And so what Hastings actually did in 2007 is he gave a rigorous proof of the area law for 1D systems. And what he in fact showed is that that the entanglement entropy is bounded by this constant. It's some exponential in log d over epsilon, where d is the dimension of each particle and epsilon is the spectral gap. So it's a constant because, of course, it doesn't depend upon the number of particles. So the Hastings proof was actually, it was a bit challenging for computer scientists to understand. And so starting in 2010 with Dorit and Itai and sorry, not Itai and Landau, but with some permutation of these authors, we started taking a, we started exploring whether there was a more combinatorial proof, and that's what eventually led to this. So we eventually managed to show that this bound could be improved by an exponential factor to log cube d over epsilon. And that's what led to this sub-exponential algorithm. OK, so now this, this result, in a certain sense, it's, in a certain very interesting sense, it's also an optimal result for a 2D area law. OK, it's optimal in the sense that this is the hardest you can work without proving anything non-trivial about the 2D case. Okay, so what that means is that if you could improve this 3 to even 3 minus delta, you'd get a non-trivial subvolume law for 2D systems. And of course, if you are thinking is that if you could reduce it to 2, then you would actually prove the 2D area law. Okay, but this.
For the 2D systems, the boundary itself is fairly large compared to the 1D system. No matter how large it is, the boundary is
only constant, yeah.
And here the boundary is about square root. So
that's right.
Is it as useful for 2D system as for 1 system?
Yeah, so you should think of the area law as not just saying that the entanglement entropy is bounded by the surface area, but the moral version of it, which says that the entanglement sits near the boundary. And as long as the entanglement is local near the boundary, so you'd have to assume that there's something more you have to prove beyond just the entropy. Even in 1D, you have to prove something beyond just the entropy bound to get something useful out of it. But then you might hope that it really gives you something useful. Okay, so by the way, this is another very fundamental open question in this area. Okay, so let me spend about 5 minutes telling you about these results and how they are proved. I would suggest the Soviet system here in this part of the talk, where the joke used to go, they pretend to pay us and we pretend to work. So I'll pretend to tell you about the proof and you'll pretend to nod and understand it. Okay, so how does this, in order to prove the area law, the main object that we use is what's called an AGSP, an approximate ground state projector. So what this does is it's an operator that leaves the ground state alone and it shrinks the orthogonal space. And it also increases, if you are interested in this particular cut, this is the boundary that we are interested in, then it doesn't increase the entanglement rank across this boundary very much. Okay? So in other words, if the shrinkage is delta and the entanglement rank increases by d, then d times delta is less than a half. So there's this trade-off between, it shrinks more than it increased the entanglement rank. And so in these terms, you can actually go back and understand, how, let me try to show you what this, why there was this belief that finding these ground states was difficult. So basically, Matt's result showed that for gap 1D Hamiltonian, you have this succinct description of the ground state. But then it wasn't clear how else you could use the gap condition. And so what the Shok, Chirac, and Vestrate result showed is that if if you were told that there's a there's a state which has a small description as a matrix product state, and you are asked to find that state, then that's NP hard. Okay, that's the difficult problem. Whereas the new result actually goes through this AGSP, and it says, the gap implies an AGSP, which implies the succinct description, and the algorithm actually uses this AGSP to find this succinct ground state. Okay, so that's the that's where where some of the extra power comes in. Okay, so how am I doing on time?
20 minutes.
Oh wow. Okay, so I can slow down.
15 with 5 minutes.
He's compacting your space.
Okay. All right. So let me see. Okay. So I'll spend 2 or 3 minutes sort of describing to you the algorithm at a high level, and then we'll go on to the next vignette. Okay. So how does this algorithm work for finding 1D ground states? So it goes like this. So first of all, if you're trying to find the ground state of a Hamiltonian H, you can easily write out a semi-definite program to find the ground state, where you say the ground state, the density matrix is rho, and then rho satisfies these conditions. Rho is positive, trace 1, and then you're trying to find that state which minimizes trace H rho. Okay, this is a semi-definite program. You can solve it in time polynomial in the dimension. Unfortunately, the dimension is exponentially large. So that's really the problem. So at a high level, what the algorithm does is it creates a polynomial dimensional envelope within which the solution is guaranteed to lie. And then we just work within that polynomial dimensional envelope and solve this semi-definite program and get the, and thereby find the ground state. Okay, so it all reduces to finding this small dimensional envelope. So how do we do that? So this is where the 1D structure becomes really critical. So in the classical case, if you have this sort of a 1D problem where you have constraints between nearest neighbors, and each of these variables takes on one of D values, then the way you can solve this is by guessing the value in the middle. So you enumerate all possible D values, but then once you guess the value 3 in the middle, it breaks up the problem into 2 pieces, right? The left part and the right part. They have nothing more to do with each other. And so now you can solve it using one of several ways, either dynamic programming or divide and conquer. Okay, so quantumly we want to do something similar. But now the problem is that you can't really guess the middle value by itself. And if you try to guess the relevant value, you realize that there's a trade-off between how many subproblems you create and the amount of error you incur. So if you want to incur an error of only 1 over n while dividing up the problem, then the number of subproblems you have to create is exponentially large in n. And so that's no good. But on the other hand, if you achieve error less than 1 over n, then that's the problem, because you're going to have to do this n times. There are n places you would cut. And so if each time you incur an error larger than 1 over n, then that's already a problem. So the main idea for dealing with this is to do this. Instead of starting with 1 over n error, we actually do this approximate decoupling with constant error. And so now the number of pieces that we create is not exponential but polynomial. Okay, but now we have to drive down the error to being 1 over n, or 1 over polynomial in n. And so to do this, we use the AGSP. Okay, because the AGSP remember what it does, it leaves the ground state alone, and it shrinks everything perpendicular to it, so it drives down the error. Okay, so but now there's a bit of a problem here, because okay, so remember what we are doing is, we are applying this procedure only to the left half of this, to the left of this boundary. And so when we apply the AGSP to the left of this boundary, we proliferate the number of subproblems. And so this is where we go back and forth. We use the AGSP to reduce the error, then we use this approximate decoupling at the next step, again to reduce the number of subproblems, and we keep going back and forth. And this is what makes sure that that this envelope stays polynomial size as we move from left to right. And then when we are done, we still have a polynomial size envelope, and we solve the STP, and that's the solution. Okay, so I finished my part of the bargain of pretending to tell you, and it's up to you now. Okay, so let me now turn to the last vignette, which has to do with testing quantum mechanics. So at least from the vantage point of computer science and complexity theory, one could say that this exponential growth of quantum systems, the exponential growth in complexity, is the most counterintuitive aspect of quantum mechanics. Now, and on the other hand, if you look at the history of physics, testing physics in the limit of various parameters has always proved to be very useful. In the limit of high energy, or very small size, or speed of light, very large velocities. It's led to interesting new kinds of physics. And so one could say, well, this kind of this new kind of limit, of large complexity, this should be another interesting limit in which to test quantum mechanics and see if it actually works. But now, once you start thinking about this, you realize that there's a of course there are many problems with this of a practical nature, but in fact there's even a problem of a fundamental philosophical nature that arises with this, which is how would you actually go about doing such testing? So meaning so if you look at the standard scientific method, it says, well, if you want to test something, you want to test a hypothesis, what you would do is you predict some outcome, of an experiment. So you design an experiment, and then you sit down and calculate what the outcome of the experiment should be. And then you actually go and perform the experiment and see if it checks out to within experimental error. So the difficulty with this is that, is of course, how do you theoretically predict the outcome if you have exponential complexity already? Right, so this is the flip side of the coin. In the previous part of the talk, I was focusing on this question. Which part of quantum mechanics can you actually do? Is actually tractable? Is computable efficiently, so that you could actually do physics and you could actually understand those systems. Right, but this is sort of saying, well, but if you look at textbook quantum mechanics, it tells you that there's exponential complexity, and now what if we take it seriously and we want to investigate that? Well, then there seems to be a problem. So there's this very interesting technique in complexity theory called interactive proofs, where there's a prover, there's a verifier who's polynomial time bounded, realistic. And then there's a prover who is a mythical creature, Merlin, who is incredibly wise and incredibly powerful, but not necessarily trustworthy. And so the question is how can Arthur be convinced about things that he doesn't really have the computational power to figure out on his own, but with Merlin's help, even though Merlin is untrustworthy. Okay, so in quantum mechanics, Merlin could be nature or your quantum experiment, and now it's no longer a mythical being. And so you could think of Arthur as your experimentalist who is polynomial time bounded. Nature is extremely powerful, and now instead of thinking of the experiment and calculating how what the answer is going to be before doing the experiment, you could actually think of a much more civilized procedure where you go to your lab and you have a nice conversation with your experimental apparatus, back and forth many times. You flip random bits and you talk to it and it answers. And at the end of that, you want to be convinced that actually your theory is correct, that nature is consistent with your theory. Okay, now these interactive proofs can be extremely powerful. They are as powerful as p-space, which is certainly much more powerful than quantum polynomial time or quantum computation. But the problem with these interactive proofs that are this powerful is that they assume that Merlin is this powerful as p-space. And so if you have this real open question, well, can a quantum polynomial time bounded Merlin actually convince Arthur about the correctness of anything in quantum polynomial time? So there's this very beautiful work by Dorit and Mickey and their student Iban, where they considered this question where with a slight twist to it, where in addition to Arthur talking to Merlin classically, there's also a small quantum channel, meaning that Arthur has the ability to work with 2 or 3 quantum bits and has a channel where he can keep sending and receiving these 2 or 3 quantum bits. So he can store 2 or 3 quantum bits altogether and can communicate back and forth. And in this model, and they showed that in fact it's possible to, for Arthur to convince himself of the correctness of any quantum computation at all. There's a similar proposal based on measurement-based quantum computation, and very recently with Ben and Falk, we showed that in fact you could also achieve this sort of result if you had not 1 but 2 Merlins, so 2 quantum experiments which have the constraint that they cannot talk to each other, they cannot communicate with each other, but they are entangled with each other. They share entanglement. So I want to spend the last few minutes describing a little bit about this result, because it goes beyond this setting, and so it actually ends up looking more like this. So you have a classical experimentalist who communicates with these 2 black boxes. These are your quantum devices, which are completely untrusted. They share Bell states or APR pairs, so entangled qubits and maximally entangled qubits. And then the experimentalist asks a series of questions, which are bits, x1, y1, and gets back a series of answers, which are bits, a1, b1. Right? And they carry on this conversation for a certain number of steps. And then Arthur does some simple test on this classical communication. And at the end of this, what Arthur wants to be convinced of is that these devices were initialized the way they were supposed to be, and that the dynamics were exactly what they were, so he wants to be sure that he can actually command them to perform a certain quantum evolution, starting with a certain quantum state and going through a certain quantum evolution. even though each of the boxes is completely untrusted. So what this result is based on is the famous CHSH game, or the Bell inequality. So, you can think of it as a game where Alice and Bob share a Bell state, and the verifier asks a random question x, a random bit x to Alice, and a random bit y to Bob, gets back A and B. And then what these two untrusted devices are trying to do is they're trying to maximize the chance that a certain condition holds. And basically, in this game, the result is that classically it's impossible to do better than 3/4, whereas quantumly, if they share this Bell state, then they can achieve a success probability of 0.85. This is the standard Bell inequality. Now, the first step in doing what we did was realizing that there's a rigidity theorem about this inequality, which looks like this. So what it says is, if these devices, Alice and Bob, actually win with probability close to the maximum, 0.85, then there's only one way to do it, essentially. Right? So there are many ways to succeed a little bit, but there's essentially only one way to succeed, optimally, which is that they share a Bell state, exactly 0, 0 plus 1, 1. And they perform exactly the prescribed measurements on input 0 and 1, respectively. Of course, how they choose to store their qubits is up to them. So, all this is up to a unitary change of bases on Alice's space and on Bob's space. Now, the multigame rigidity theorem says that this holds even if you play a number of sequential games. So in the multigame rigidity theorem, what happens is that the verifier or the experimentalist just plays a sequence of such games, many games, one after the other. And now the theorem says that if Alice and Bob win close to 85% of the games, then they must share a tensor product of Bell states, in tensor product with everything else in their spaces, and they must perform measurements according to prescription. Now, once you have this sort of thing, it's a little bit like, I don't know if you've ever seen an Aikido demonstration where there's a little Japanese Aikido master who's throwing around this big hulking fellow, and at some point he gets his opponent in this kind of hand lock, and once it's like that, then it's all over, right? Anything that this person does is so painful, So basically, this little master sort of, takes him through any kind of movement, and this fellow has to follow exactly what he's doing. So this is exactly what this multigame rigidity theorem does. You have this little fellow who gets these big hulking quantum systems into this hand lock, and then once you can make sure that they must perform exactly these particular transformations, you can. Then you can force them to do exactly what you want. That's sort of an easy thing. Let me sort of, just say that there's a correspondence between what's done with these multigame rigidity theorems and what's called the classical multilinearity tests. So these are components of the PCP theorem, and what they are simple local tests that allow you to verify that a function that two provers are thinking of, now classical provers are thinking of, is a linear function, some linear function. So again, the object is exponentially large. It's a linear function on some space, and you can test that it's close to linear while testing only a constant number of spaces. Something similar is happening here, because you want to test that the state of 2n qubits is exactly what it's claimed to be, up to some unitary change of bases on each side. And by doing some simple tests, you can actually verify that, and you can even verify the measurements that are done on each side. There's actually a different generalization of this classical multilinearity test that Thomas will speak about tomorrow, which is actually another very beautiful generalization. In this case, the shared object is classical, where so it actually is a straight generalization of this in the context of quantum provers, whereas here the shared object is quantum itself. Okay, so just to recap, there were three questions that that I touched upon. The first was whether we can understand and simulate natural quantum systems, and the second, whether quantum systems can exhibit exponential complexity at high temperature, and the third was whether the scientific method is sufficient to actually understand general quantum systems. And the point is that once you view these three questions computationally, they really end up being questions about computation. And the proof of that is that you can write 3- and 4-letter acronyms describing them. So the question about high temperature is really whether there's a quantum PCP theorem.
Well, what is high temperature? Any constant temperature above zero?
Yeah. This question about simulating natural quantum systems turns out to be about what's the structure of solutions to this quantum analog of satisfiability. And this question about the scientific method is a question about quantum interactive proofs with quantum polynomial time verifiers. So let me just finish by saying that in spring 2014, we have a workshop, a program at the Simons Institute in Berkeley for the semester, dealing with this topic of quantum Hamiltonian complexity. Dorit is co-organizing the program, and there are 3 workshops dealing with this general area. So many, some of you are already slated to participate in the program, but if others are interested, please do let us know, and it should be a party. Okay.
Time for a couple questions.
In the first part, you talk about this ability to describe objects. And I wonder if this is a valid criteria for I'm thinking of several. Even if I have a single cubic state, I need infinite amount of information to describe it. Here. So if I have a single qubit, I need an infinite amount of information to describe it.
Yeah.
But I still can get a lot out of it.
That's right. So I guess the question is, this is really a question about digital versus analog information, right? So how much information can you store in one quantity? And I guess a lot of people have addressed this, but Feynman, of course, did in one of his papers where he talked about the fact that, look, if you look at the most exquisite measurement ever done, how much do you get? You get 10, 12, 13 decimal places. If you do it indirectly using incredible amount of effort, you get 14, 15 decimal places. Well, how many bits is that? That's, it's 100 bits. Okay, so basically, as far as that's concerned, you may as well assume that any single quantity is less than 100 bits. And then, complexity theorists don't care about 100 bits, factors of 100.
Yeah, I have a question.
Sorry.
Oh, pass the mic. Where is
Thank you.
Grateful?
He just stepped out.
You seem to harbor a suspicion that maybe at large scales quantum mechanics will break down. I mean, that's what you're sort of investigating, I think, because you're kind of accepting the fact that at very small scales it's okay. So, you know, when you talk about over 100 bits and stuff, you're thinking that maybe somehow quantum mechanics breaks down at large scales. And I was wondering, you know, the world around us looks classical, and do you have a sense that maybe the complexity theorists shed any light on why the world looks classical when at base it's quantum mechanical? Do you think that's a breakdown in quantum mechanics or a breakdown in something, or does it just require some kind of understanding?
Well, you know, I would say it's simpler than that. I would say that it's just a much simpler question, which is, you know, it just has to do with the scientific, you know, how one does science. You know, if you have a, you know, if you take sort of the Popperian view of science seriously, you would say that really the extent to which you believe a scientific theory is the extent to which you test it. And so, and you know, and you should really test the most counterintuitive aspects of the theory. So to the extent that we believe, you know, that we feel that this you know, exponential complexity is a counterintuitive aspect of quantum mechanics, it's really almost our duty to go and test it as rigorously as possible, right? And so that's the, you know, that's the basic motivation.
Yeah, but I still want to know if you think that it's possible there's some reason the world looks classical that has to do with something, with a breakdown in quantum mechanics of when you go to large numbers of particles.
But that would be icing on the cake. If you know, if one were to discover that that somehow, you know, so for example, if one were to investigate this and if it did not scale, then it would be interesting to see in what way it doesn't scale. But I think the first thing that is clearly important is just to test.
Okay, we better move on. Sorry. Our next speaker is
You should get this out of here,
Hans
right?
Briegel.
This is you?
Oh, no, that's. Here, Hans.
Okay.